Good morning. Today, I want to talk to you about running transformer models on the M1 Mac in their native format. Uh, so, if you run in Python, it's very likely that you're going to be running in Huggingface's native format, and that's not optimized for the Apple Neural Engine. So we want to reformat this transformer model into a data structure that can be used efficiently on the Apple Neural Engine. And when we do this, we move the model off the CPU and off the GPU onto the ANE, where it can run on 16 cores rather than on 8, and where we keep the CPU and GPU free so that they can do whatever processing they need to do for other tasks. Now let's run over to the desktop and we can get started on this. So first of all, I want to point to this article here, deploying transformers on the Apple Neural Engine. And this is fairly new. This is from June 2022. And it's on Apple's own website here, machinelearning.apple.com/research/neural engine transformers. I guess that's the whole URL for it. But if you do a Google search for deploying transformers on the Apple Neural Engine, you should find this article pretty easily. Now, there is, I believe, one step missing in this article, so I'll point that out to you. Might as well read through this while we're here. Let me just kick this off.
Increasing number of the machine learning ML models we build at Apple each year are either partly or fully adopting the transformer architecture. This architecture helps enable experiences such as panoptic segmentation in camera with Hyper-DETU, R on-device scene analysis in photos, image captioning for accessibility, machine translation, and many others. This year at WWDC 2022, Apple is making available an open-source reference PyTorch implementation of the transformer architecture, giving developers worldwide a way to seamlessly deploy their state-of-the-art transformer models on Apple devices. This implementation is specifically optimized for the Apple Neural Engine ANE, the energy-efficient and high-throughput engine for ML inference on Apple Silicon. It will help developers minimize the impact of their ML inference workloads on app memory, app responsiveness, and device battery life. Increasing the adoption of on-device ML deployment will also benefit user privacy, since data for inference workloads remains on-device, not on the server. Principles behind this reference implementation to provide generalizable guidance to developers on optimizing their models for ANE execution. Then we put these principles into action and showcase how to deploy an example pre-trained transformer model, the popular Huggingface to Stillbert, in just a few lines of code. Notably, this model, which works out of the box and on device using coreml already, is up to 10 times faster and consumes 14 times less memory after optimizations. Published in 2017, the transformer architecture has had a great impact in many fields, including natural language processing and computer vision. In a short period of time, models built on this architecture produce state-of-the-art results across a wide spectrum of tasks while anchoring little to no domain-specific components. This versatility has resulted in a proliferation of applications built on this architecture. Most notably, the Hugging Face model hub hosts tens of thousands of pre-trained transformer models, such as variants of GPT-2 and BERT, which were trained and shared by the ML community. Some of these models average tens of millions of monthly downloads, contributing to the research momentum behind training bigger, better, and increasingly multitask transformer models. and giving birth to the development of efficient deployment strategies on both the device side and the server side.
Before we move on, I just want to point out to you this bit here. This model, which works out of the box and on a device using coreml already, is up to 10 times faster and consumes 14 times less memory after our optimizations. So that is a big gain. To get an order of magnitude faster speed is no small thing. So this is definitely worth doing. It's easy enough to run these Huggingface models in Python, but that's just not the Apple way. What we want to do is we want to convert them into Apple's format and then run them in Swift.
Neural Engine. The first generation of the Apple Neural Engine was released as part of the A11 chip found in iPhone X, our flagship model from 2017. It had a peak throughput of 0.6 teraflops, T-flops in half-precision floating-point data format, Float16 or FP16, and it efficiently powered on-device ML features such as Face ID and Memoji. Fast forward to 2021, and the fifth generation of the 16-core AIN is capable of 26 times the processing power, or 15.8 T-flops of the original. Since 2017, use of the AIN has been steadily increasing from a handful of Apple applications to numerous applications from both Apple and the developer community. The availability of the Neural Engine also expanded from only the iPhone in 2017 to iPad starting with the A12 chip, and to Mac starting with the M1 chip. When training ML models, developers benefit from accelerated training on GPUs with PyTorch and TensorFlow by leveraging the Metal Performance Shader's MPS backend. For deployment of trained models on Apple devices, they use coreml tools, Apple's open-source unified conversion tool, to convert their favorite PyTorch and TensorFlow models to the coreml model package format. Coreml then seamlessly blends CPU-GPU and AIN if available to create the most effective hybrid execution plan exploiting all available engines on a given device. It lets a wide range of implementations of the same model architecture benefit from the AIN even if the entire execution cannot take place there due to idiosyncrasies of different implementations. This workflow is designed to make it easy for developers to deploy models on Apple devices without having to worry about the capabilities of any particular device or implementation.
So it looks here as though training will occur most efficiently on the GPU, Apple's Metal Performance Shaders. However, for inference, we want to use coreml tools, which are going to use all three units of the M1 chip, the CPU, the GPU, and the ANE if available. So there will be hybrid execution, but I think that just from just the way you think about this is it's going to run primarily on the ANE if you use coreml tools. And of course, coreml tools are loadable using Swift, and they're available using the Swift language or also Objective-C, which I don't really know too much about. I find that Objective-C is just a big pain in the neck, and the Swift it takes away a lot of the pain, but doesn't lose much of the performance.
Behind optimizing transformers for the neural engine. Although the implementation flexibility that hybrid execution offers is simple and powerful, we can trade this flexibility off in favor of a particular and principled implementation that deliberately harnesses the AIN, resulting in significantly increased throughput and reduced memory consumption. Other benefits include mitigating the inter-engine context transfer overhead and opening up the CPU and the GPU to execute non-ML workloads while AIN is executing the most demanding ML workloads. In this section, we describe some of the generalizable principles behind our reference implementation for transformers with the goal of empowering developers to optimize models they intend to deploy on the AIN. Principle 1. Picking the right data format. In general, the transformer architecture processes a 3D input tensor that comprises a batch of B sequences of S embedding vectors of dimensionality. See, we represent this tensor in the BC1S data format because the most conducive data format for the AIN hardware and software stack is 4D in channels first. The native torch and in transformer and many other PyTorch implementations use either the BSC or the SBC data formats, which are both channels, last and 3D data formats. These data formats are compatible with N in linear layers, which constitute a major chunk of compute in the transformer. To migrate to the desirable BC1S data format, we swap all N in linear layers with N in COM2D layers. Furthermore, to preserve compatibility with previously trained checkpoints, using the baseline implementation, we register a load state dict3 hook to automatically unsqueeze the N in linear weights twice in order to match the expected and NCOM2D weights shape, as shown here.
All right, well, I'm gonna break off here because this is really the important thing that you need to understand is that the ANE wants this data format here. So this extra channel here, this one, is added in to either the BSC or the SBC data formats. And of course, they are both of these formats are converted to this format when we something you'll see in the notebook I've prepared. And so I'm going to skip down through here. You can read this if you want to understand more about that, and then of course go to all of these links here. But this is how shall I put this? Uh, if you just want to know how to use this, understanding all of the rest of this, I don't think is uh, necessary. So I think you can skip all of this here. So let's pick it up here.
Study, Huggingface to Stilbert. As the scaling laws of deep learning continue to hold, the ML community is training bigger and more capable transformer models. However, most open source implementations of the transformer architecture are optimized for either large-scale training hardware or no hardware at all. Furthermore, despite significant concurrent advancements in model compression, the state-of-the-art models are scaling faster than compression techniques are improving. Hence, there is immense need for on-device inference optimizations to translate these research gains into practice. These optimizations will enable ML practitioners to deploy much larger models on the same input set, or to deploy the same models to run on much larger sets of inputs within the same compute budget. In this spirit, we take the principles behind our open source reference PyTorch implementation for the transformer architecture and apply them to the popular Distilbert model from the Hugging Face Model Hub in a case study. Applying these optimizations resulted in a forward pass that is up to 10 times faster with a simultaneous reduction of peak memory consumption of 14 times on iPhone 13. Using our reference implementation on a sequence length of 128 and a batch size of 1, the iPhone 13 achieves an average latency of 3.47 milliseconds at 0.454 W and 9.44 milliseconds at 0.072 W even using our reference implementation. The AIM peak throughput is far from being saturated for this particular model configuration, and the performance may be further improved with using the quantization and pruning techniques as discussed earlier. Numbers we just reported. A recent article from Hugging Face and AWS reported the average latency is 5-6 milliseconds for a sequence length of 128 for the same model in our case study, when deployed on the server side using ML-optimized ASIC hardware from AWS. Based on this external data point, we are happy to report that our on-device inference latency compares favorably to those measured on an optimized server-side inference engine while executing on a device that is orders of magnitude more energy constrained. Figure 2 shows the latency and memory consumption of the same model across different sequence lengths, batch sizes, and devices.
That's quite a difference from here to here. I guess this is over a second, and this is far under a second. It looks like about 200 milliseconds is the slowest, based on 164 milliseconds based on a batch size of 8. So that's pretty incredible. All right, so let's see here.
Altogether from PyTorch to Xcode. Finally, we show how these optimizations are applied through just a few lines of code. And then we profile the model in Xcode using the new coreml performance report feature available in Xcode 14. To begin, we initialize the baseline Distilbert model from the Huggingface model hub.
All right, so this is all pretty standard, using the auto model for sequence classification from pre-trained. We're going to grab this checkpoint here, and then
we initialize the optimized model, and we restore its parameters using that of the baseline model to achieve high output parity as measured by peak signal to noise ratio, PSNR.
all right, so this here is where the omission lies. From A&E under transformers.huggingface, import Distilbert as A&E Distilbert optimized model, blah, blah, blah. So you have to do a pip install A&E transformers to get this working. And then you have to import A&E transformers. So if we run over to VS Code here, we could take a look at this. This is the first cell, and that's just basic Hugging Face stuff. But here we import the A&E transformers, and then we run the rest of this. So if you don't do this and you don't do the pip install, it's not going to work. So you can see here I'm in this Bloom 2 virtual environment. And within the terminal here, that's where I did the pip install A&E under transformers. So do that first, and then add the import A&E under transformers, and then you can copy in the rest of that cell and run it. And you see it outputted here. All keys match successfully. And let's go back here. And we create sample inputs for the model here. So here's what we're creating here: a sample input text to trace the model, and we can see here let's take a look at the output. We're not getting the output here. Let's add it. So I'm going to just do a B here. I'm going to his no. I'm going to do just a escape and B. That inserts a cell below here, and then tokenized. Shift Enter. All right, where to go? Uh, oh, here we are. So this creates this tensor here. These are the tokens for it. So here's like the begin sequence and end sequence, and then these tokens are in here. And here's the attention mask for it. So these guys are actually something you need to look at, and the rest of this is padding. Uh, I'm not sure what this torch.jit.traits method is doing here. But we're using the optimized model, which is I believe, still the Huggingface format. And here's our tokenized input IDs and attention mask. So I'm not sure what's it's pulling out of there. And it's giving us an error here. Well, it's not an error, but it's a warning. Uh, so I guess this is creating a trace, and I think it's saying that don't reuse this trace for anything else. Uh, and here's the good stuff coming up here. Import core ML tools as CT. So yeah, I'm not sure where core ML tools exists because we didn't have to do a pip install of core ML tools. So I suppose that maybe when we did the transformers under A&E uh, pip install, maybe core ML tools was also grabbed. So we can check that here. Uh, if I do a pip list and grep for core, see we've got core ML tools. Now I did not load those. So I'm guessing that when I did the pip install, let's see, pip install A&E transformers. Let me run that again and see what happens here. Uh, all right, I don't want to look through all that stuff. I'm too lazy. Let me just grep for core here. Yeah, so it's putting in core ML tools for us. Uh, a TQDM also, which is it gives us a progress bar, and yeah, so that's where we're getting this import. That's why we're able to do this import core ML tools, because it's bundled into the requirements for what was that, transformers A&E under transformers. So once we bring this in here, we're bringing in NumPy also. Here's where we're doing the conversion. So yeah, I don't know what this traced optimized model object is, uh, but it's something that's required for doing that data conversion from 3D to 4D. Uh, and so we're converting to an ML program, and yeah, so that's the important thing to understand. And then of course it goes through and does a whole bunch of stuff here. And what we end up with is, yeah, I don't know why this didn't work. Uh, what we end up with is Here's an ls of the directory that this is all being done in. And so here's the notebook. And here is Huggingface A&E Transformers Distilber sequence length 128 batch size 1.ml package. And this .ml package file can now be imported into an Xcode project and can be accessed using ML Core. So this is what we're after. We're after this is our model in ML package format, which is Apple's own format for neural network models. Now, I will be doing a future video that shows how to use this. I suppose that immediately, if you just want to test it, you can go into coreml and do it there. Can I pull this up this way? No, it's not coming up this way. So if you go into Xcode here, where is coreml? I'm not sure how to, I don't remember how to open up coreml from here. It's easy enough to look up. Well, I'm not going to take any more time with this because I've got a video that shows how to work with coreml uh, using their own, I guess it's an IDE for coreml. Uh, and it's really it's machine learning for dummies. It's just really easy, but I don't remember how to do it offhand. Uh, Maybe it's createml. Createml, I guess, is the tool here. Uh, so you can just take a look at my video on createml or look up createml, and you can test that model. And so I'll be doing that in a future video, and I'll also be showing how to access the model from an Xcode project because I'm going to need to run one of these. I wanted to create a conversational AI service, and so I'm going to be doing that in Xcode and writing it in Swift. Both the client and the server will be written in Swift. So that's coming up. And for now, that's it. And I thank you for joining me. And I hope you found this interesting. Bye bye.